In this chapter, we will discuss the basics of measurements and experimentation in physics. We will learn about different types of physical quantities, their units, and how they are measured. We will also be learning about simple pendulum. Physical quantities are properties of objects or phenomena that can be measured. For example, we can measure the length of a cricket pitch using a measuring tape, or the mass of an object using a balance. Any measurable property in physics is a physical quantity. Physical quantities are classified into two main types: fundamental quantities and derived quantities. Fundamental quantities are independent and cannot be derived from other quantities. Derived quantities are obtained from one or more fundamental quantities. The 7 fundamental quantities in the SI system are length, mass, time, temperature, electric current, luminous intensity, and amount of substance. Here is a table showing each fundamental quantity, its SI unit, and its symbol. Learning these is important as all other units in physics are built from these fundamental quantities. Length. Length is the measure of distance between 2 points. It can be measured using rulers, measuring tapes, or more advanced devices depending on the accuracy required. Mass. Mass is the amount of matter contained in an object. It is measured using a balance. The SI unit of mass is kilogram. Time is the measure of the ongoing sequence of events. It is measured using devices like stopwatches or clocks. The SI unit of time is second. Temperature measures how hot or cold an object is. It is measured with thermometers. The SI unit is Kelvin, although Celsius is also commonly used, but the SI unit is Kelvin. Luminous intensity is the measure of the brightness of a light source in a particular direction. Its SI unit is candela. The amount of substance refers to the number of particles, atoms, molecules, or ions in a sample. The SI unit is the mole, which is defined as containing 6.022 multiplied by 10 raised to 23 particles. Now let's move on to derived quantities, those that come from combining fundamental quantities. The area of a square is calculated by multiplying length by length. Since length is measured in meters, the unit of area becomes meter squared. Here is an example. If the length of a table is 3 meters and the breadth is 2 meters, its area is 6 meter squared. Volume is another derived quantity. For a cube, volume equals length multiplied by length multiplied by length, or side multiplied by side multiplied by side. If each side is measured in meters, the unit of volume is cubic meters. Speed is calculated as distance traveled divided by the time taken. The SI unit is meter per second. Acceleration is the rate of change of velocity with respect to time. It is calculated as change in velocity divided by time. In SI units, acceleration is measured in meters per second squared. Density is defined as mass per unit volume. The formula is density equal to mass divided by volume. For example, if we have a cube of mass 1 kg and each side is 1 meter, the volume is 1 meter cube. So the density is 1 kg per meter cube. The SI unit of density is kilograms per cubic meter. Force is a push or pull that can change the motion of an object. The formula is force equal to mass multiplied by acceleration. If we insert the SI units, We have kilogram multiplied by meter per second squared, giving the units kg meter per second square, which is also called the Newton. Pressure is defined as force per unit area. Formula is pressure is equal to force divided by area. Using SI units, force is in newtons, area is in square meters, so it should be Newton per meter square. Also, you can keep kg meter per second square for force and meter square for area. You would get kg per meter second square. This I already described. Newton for force and meter square for area. And Newton per meter square is also called Pascal. Pressure tells us how concentrated a force is over a given area. Units are divided into two categories: fundamental units, which are independent and not related to other units, and derived units, which depend on fundamental units. For example, meter for length is a fundamental unit, while meter per second for speed is a derived unit. Here are examples of derived quantities and their SI units. Volume in cubic meters, density in kilograms per cubic meter, speed in meters per second, and acceleration in meters per second squared. Each of these is expressed in terms of the fundamental units. The least count of a measuring instrument is the smallest measurement it can take accurately. For example, a meter scale has a least count of 1 millimeter or 0.1 centimeter. Instruments with a smaller least count can measure more precisely. Here is a 10 centimeter ruler. It is divided into 100 equal parts, each representing 1 millimeter or 0.1 centimeter. Now you can see that it is divided into 10 equal parts between each centimeter mark. Each small division represents 1 centimeter divided by 10, which is 0.1 centimeter. That is equal to 1 millimeter. Smaller the least count, the more accurate the measurement. In this case, the smallest length measured accurately is 1 millimeter. The vernier calipers is a precision instrument used to measure length more accurately than a standard ruler. It has a typical least count of 0.01 centimeters, making it much more precise. The vernier calipers consists of inside jaws for measuring internal dimensions, outside jaws for measuring external dimensions, and a depth rod for measuring depths. It also has a main scale and a vernier scale to read the measurements accurately. We can use vernier calipers to measure length or thickness of an object. We can also use it to measure inner diameter of hollow objects like pipes. We can measure depth of holes or cavities. Its versatility makes it essential in laboratories. The least count of a vernier calipers is calculated using the formula least count is equal to value of one main scale division minus value of one vernier scale division. For most standard vernier calipers, this works out to be 0.01 centimeter, enabling very fine measurements. One more formula that you can see, least count is equal to value of one main scale division divided by total number of divisions on vernier. The least count of a vernier calipers is the difference between the value of one main scale division and one vernier scale division, right? So least count is equal to Value of 1 main scale division is 1 millimeter, and in this case value of 1 vernier scale division is 0.9 millimeter. Therefore 1 minus 0.9 is equal to 0.1 millimeter. Also, least count is value of 1 main scale division divided by total number of divisions on vernier. So, value of 1 main scale division is 1 millimeter divided by total number of divisions on vernier. It is 10. So, 1 divided by 10 equal to 0.1 millimeter. Or you can say 0.01 centimeter. When measuring, we note which vernier scale division exactly coincides with a division on the main scale. This helps us determine the fractional part of the measurement beyond the main scale reading. In this case, the 9th division coincides with a division on the main scale. Let's solve a problem. The value of 1 main scale division is 0.1 centimeter, or you can say 1 millimeter. The vernier has 10 divisions. So the least count of vernier is value of 1 main scale division divided by number of divisions on vernier scale. So least count of vernier is equal to 0.1 divided by 10, which is 0.01 centimeter, or you can say 0.1 millimeter. Suppose the main scale reading is 3.2 centimeter. Before 0 of the vernier scale, you can see 3.2. 7th division coincides with the main scale division. And let's say it is P. So P is equal to 7. 7th division of the vernier scale coincides with a division on the main scale. The other divisions are not coinciding. This seems to be coinciding quite nicely. Vernier scale reading is equal to P, the coinciding division, multiplied by least count, which we have already calculated. So 7 multiplied by 0.01, which is equal to 0.07. Total reading is main scale reading plus vernier scale reading. What's the main scale reading? It is 3.2 and vernier scale reading is 0.07. So 3.2 plus 0.07 gives you 3.27 centimeters or 32.7 millimeters. Zero error. Zero error occurs when the zero mark of the vernier scale does not coincide with the zero of the main scale when the jaws are fully closed. If the vernier zero is to the right of the main scale, we say that there is positive zero error. If it's to the left, it's a negative zero error. Screw gauge. Screw gauge is a precision instrument used to measure very small lengths or thicknesses, often up to hundreds of a millimeter. It consists of a main scale, circular scale, and screw mechanism for fine adjustments. You can see the other parts here. Now, pitch of a screw gauge. The distance moved by the screw along its axis when the circular scale is rotated through one complete revolution. If one rotation moves the screw forward by 1 millimeter, pitch is 1 millimeter. Number of divisions on the circular scale allows for very fine measurements. Least count is pitch of screw divided by total number of divisions on its circular scale. So least count is equal to 1 millimeter divided by 100, which is 0.01 millimeter. Like vernier calipers, screw gauges can have zero error. If the zero mark is below the baseline of the main scale, zero error is said to be positive. If the zero mark is above the baseline of the main scale, zero error is said to be negative. A simple pendulum consists of a heavy point mass called the bob, suspended by a light inextensible string from a fixed support. It swings back and forth under the influence of gravity. Oscillation, one complete to and fro motion. Time period, time taken for one oscillation. Frequency, number of oscillations per second. Amplitude, maximum displacement from the mean position. These terms are crucial when you are learning about pendulum. Relationship between time period and frequency. Frequency is equal to 1 divided by time period. This means that as the time period increases, frequency decreases. F equal to 1 by T. Time period is equal to 1 by frequency. So T is equal to 1 by F. Expression for time period. Time period is given by the formula T equal to 2 pi root L divided by G. L is the effective length and G is the acceleration due to gravity. The time period of a pendulum is directly proportional to the square root of its effective length, and it is inversely proportional to the square root of the gravitational acceleration. Importantly, it does not depend on the mass of the bob or the amplitude of the oscillation. A seconds pendulum is a pendulum with a time period of exactly 2 seconds. 1 second for a swing in one direction and 1 second for the return. At a place where G is 9.8 meters per second square, its effective length is close to 1 meter. A simple pendulum completes 40 oscillations in 1 minute. Find its frequency and time period. Frequency F is equal to number of oscillations divided by total time. Number of oscillations, it is equal to 40 and total time is 60 seconds. So the frequency will be 0.67 Hertz. Time period is equal to 1 divided by frequency. That is 1 divided by 0.67, which would be approximately equal to 1.5 seconds. The time period T is 2 seconds. What is the frequency and what name is given to such a pendulum? So there is a simple pendulum having time period of 2 seconds. So that pendulum is called the seconds pendulum. Frequency F is equal to 1 by T, which is equal to 1 by 2, and that would be 0.5 second inverse, which is Hertz. Pendulum with this time period of 2 seconds is called a seconds pendulum. A seconds pendulum is taken to a place where G becomes 1/4. How is the time period affected? So time period is inversely proportional to the square root of G. So if G becomes G by 4, then the time period is doubled. You can see it becomes T multiplied by root 4. Therefore, it is equal to 2T. So if the time period is 2 seconds, then the new time period will become 4 seconds. Find the length when Time period is 2 seconds. Acceleration due to gravity is 10 meter per second square, pi 3.14. So let's find the length. So rearrange this equation in terms of L. So L will be equal to gt square divided by 4 pi square. Substitute the values and you will obtain the value of effective length, which is equal to 1.0142 meters. Compare the time periods of two pendulums of length 1 meter and 9 meter. So time period is directly proportional to the square root of its effective length. So T1 by T2 is equal to root of L1 by root of L2, which is 1 divided by 9, that would be 1 by 3. So T1 to T2 ratio is 1:3. A pendulum completes 2 oscillations in 5 seconds. What is its time period? Time period would be 5 divided by 2, which is 2.5 seconds. So it completes one oscillation in 2.5 seconds. If g is 9.8 meters per second squared, find its length. Effective length would be gt square by 4 pi square. Substitute the values, you will obtain L equal to 1.55 meters. Time periods of two simple pendulums at a place are in the ratio of 2:1. What will be the ratio of their lengths? T1 by T2 is equal to 2 divided by 1. We know that time period is directly proportional to the square root of length. So length would be equal to T square. So L1 by L2 is equal to T1 by T2 whole square, which is 2 by 1 whole squared, which is 4:1. It takes 0.2 seconds for a pendulum bob to move from mean position to one end. What's the time period of the pendulum? So it is taking just 0.2 seconds for this bob to move from mean position to one end. Okay, so from mean to one end is T by 4, right? That is just 25% of the oscillation. That's why T by 4. So T by 4 is 0.2 and time period will be equal to 0.2 multiplied by 4, which is equal to 0.8 seconds. How much time does the bob of a second's pendulum take to move from one extreme of its oscillation to the other extreme? Now from one extreme to the opposite, that is half of the oscillation. So we could say it is T by 2. So for a second's pendulum, we know that it takes 2 seconds to complete one oscillation. Time period is 2 seconds. So to complete half oscillation, it would take 1 second.